All right, so you're working on PS 11, which I may do Monday or Tuesday with a late day. PS 12 will come out tomorrow and be due a week from Monday, or a week from Tuesday with a late day. So you can choose, and there's an overlap there, so you can choose whether you want to work more sooner or later. Then the last day of class will be in, 12 days, which is a Tuesday, and then our final exam is on the following Thursday. And I'm going to see if I can interest the TAs in running a review session on Wednesday. Any interest? I'm sure that, yeah, we can get some people to do that. Any questions or problems? Yes?
Is it going to be split up like the mission was?
Oh, yes. Yes, we'll do the same split. So first part of the alphabet, I forget what it was, A through something, goes down the end of the hall. Yes?
Will we be able to bring notes?
You can bring 2 sheets of notes. Probably tomorrow I'll post an old final. Yes?
Is it 2 sheets double-sided?
2 sheets, yeah. 2 sides. Same rules as for the midterm, except 2 sheets. Yeah?
Is the final cumulative?
The final is cumulative, yeah. I'm not sure how it would make up a final just on the second half of the class. I'm glad it's cumulative. Before I forget, so in PS 11, if you can run in the following situation. So you implement your program. I guess this was a problem on PS 10 as well. I didn't think about it then. But you run the program, and what happens when your server throws an unexpected exception, null pointer exception, or something, just because you got a problem in your code? How do you find out about it? Okay, so yeah, the server will stop. How do you find out about the exception detail? Okay, so I was helping someone yesterday, and when the server was having an exception, but all that we would see is on the client we get like a 50 something, or 500 internal server error, which isn't very much to go on. So you probably want to put try-catch blocks around all your endpoints, just to catch any exception that leaks through, any unhandled exception, so that you can, then do something. Typically, what you do in a service is when you catch an unhandled exception, you would log it somewhere, so you could look at it later. But for debugging purposes, catch the exception and print it out and print out a stack trace, so that you've got a fighting chance to do the debugging. You've got to know what the exception was if you want to debug. So keep that in mind. Just don't write your code so exceptions are lost and you can't tell what happened. All right, anything else? Yes?
So what was the try-catch for that you were explaining a little bit?
Just to catch any exception that escapes from your endpoint method.
Okay.
And probably what you want to do is catch the exception, print out any relevant information, then rethrow it.
Okay.
Okay. All right, so let's think about PS 12. So like I told you last time, on PS 12, you're going to be, it's just like PS 11. It'll have mostly the implementation of PS 11. It'll have the same unit test as same grading test as PS 10, 11, and 12. And the difference is you're going to deploy it in a console project as opposed to a web API. And so you'll have to provide the code that implements a web server, an HTTP server. So essentially you'll host your existing service on your own HTTP server as opposed to the one that, IIS that comes with Visual Studio. And the good news is it's a lot easier than it sounds. So what we're going to do today is talk about what you'll need to know to do that, just to get you ready for that. So last time we looked at a pretty high level of detail at sockets, some of the methods provided by the socket class in C#. And I have built on top of that socket class something called a string socket. And the string socket is just, it's not part of .NET, so you won't find much to Google about it. And, but it's designed to make doing PS12 easier. Now, in the past, I have, the PS8 that I did this year, I'd never done before. So everything used to come a week earlier, and then PS11 was implementing the string socket, and PS12 was using it. So you got out of implementing the string socket this year. Oh, I should add, by the way, that we haven't forgotten about grading PS8. It's just taking a long time. It takes about 20 minutes for the script running on my laptop to grade one submission. So it's grading right now. So hopefully I don't overload the computer with this and cause someone to start failing tests. So. I got to steal the time somewhere. All right, so string sockets are to make your life easier on PS12. So what we're going to talk about here to start is what you get with a string socket. Okay, so we talked about last time that the heart of a server was a TCP listener, which listens for connection requests from a client, and when they come in, it establishes a socket connection with the client. So I have a class I wrote called string socket listener. It's just completely analogous to TCP listener. It listens for an incoming connection request, and instead of giving you back a socket, it gives you back a string socket. There's also a class called string socket client. We didn't talk last time. There's a class called TCP client, which is a way for a client code to obtain to connect to a remote server. But I didn't talk about it because you're not implementing a client. So for completeness, I show you the slide here. Where unless you write, you want to write unit tests using string sockets for some reason, you won't need to worry about TCP client. So that brings us to string sockets. So a string socket is an object that contains within it a socket. So just think of it as a wrapper around a socket, except the methods that it provides makes it easier to use than a raw socket. And you, instead of thinking in terms of bytes, you think in terms of strings. And the fundamental operation is, two fundamental operations are sending and receiving. So there is a begin send method. So if you want to send a string out the socket, you call begin send. You give it the string to send. You give it the callback method to call once the string has been sent. And you can give it a payload object. So the socket receives these requests. So the socket is thread safe. You can call it from multiple threads, although you won't need to. And it sends the strings out in the order in which they were provided via calls to begin send. And once they have been successfully sent, the callback method is called. Now, for your server, you're just going to send string and then another string and another string. You're not going to have multiple threads trying to send out strings at the same time on the same socket. You'll have multiple threads sending on different sockets. So that's begin send. Once the send has completed, once it's been sent through the socket, converted to bytes and sent, the callback method that you provide will be called by the socket. And the parameters are was sent, which can be either true or false. So I guess the other option is maybe the send failed, in which case this would be false. And then the payload object comes back. So in terms of your server, you'll send a line, and then when the callback is called, you'll send the next line, and when that callback is called, you'll send the next line, and so on. Now that seems pretty simple. What do you make of that payload object? What is it good for? What do you think? What interest does the begin send method have in that payload object? Right, I'll give you a hint. The string socket has no interest whatsoever in the payload object. It doesn't even look inside it. It just keeps it and sends it back as a parameter when the callback is called. So why would you, at writing code that uses a string socket, want to use a payload object? use your imagination and see.
To bundle everything to send.
Well, the only thing that's being sent is the string. And the payload object can be anything whatsoever, but it's not even looked at by the server, by the string socket. Yeah?
Sorry, what do you mean by payload?
Well, that's just up to the application programmer what I mean by payload. I just call it payload. It's just some object that you give to begin send, and it sends it back when it calls the callback.
So just so you know you're getting back the right thing.
Well, yeah, but if we're just checking to see if we get the right thing back, why bother with it?
Yeah.
Yeah.
I don't really, maybe the callback is like in a different place in the program, like inside different brackets or something, and you want to
Okay.
do a scoping issue.
Okay, so that's getting at it. The callback method is going to be running on a different thread than the begin send ran on, right? So begin send calls, and then sometime in the future on some thread, the callback is called, and the payload is passed in. Yeah.
Does it need something in the transmission?
No, it has nothing to do with. It just has to do with your needs as It has nothing to do with sockets. Yeah.
Does it have something to do with referencing where it was sent from?
Referencing where it was sent from, perhaps, depending on what you mean by that.
Sorry, that's very vague.
No, these are reasonable guess. Okay, there's a similar. If you look at the regular socket class at the begin send, there's also a payload object that can be sent around, and it's just this. You can write PS12 without it. Some people use it, some people don't. It's a way of sending state information. So you call begin send, and you realize that when this callback is called, it needs some information about what to do next, maybe like what state is the server in. One way to do that is with instance variables, and another way to do it is just pass some information. Maybe you've got a string that the callback receives, and the string tells the callback what to do next. Tells it what just happened, what should be done next. So if you need to get information from the point at which you call begin send to the point at which this callback is called, you can send it to yourself through the payload. It's just a way of passing a parameter to the callback method. So you may find a use for it. You may decide you don't. So you just pass null if you don't want to bother with that. But I'm always asked that, so I want to mention it. Okay, so it's still asynchronous, just like we saw last time with sockets. You call begin send, and that thread can die. In the future, the callback is called, and then you can pick up from there. And then receiving works pretty much the same way. To receive text, you give it a callback to call when the text has been received, and you send a payload object if you wish. And it reads a line of text. So unless length is not 0. So if length is 0, what it does is it reads bytes from the socket until it has a complete line of text terminated with a new line. And then it sends that to the callback. If, on the other hand, you give it a length, like 42, then what it will do is read 42 bytes, convert that into a string, and pass it back to the callback. So you can either ask for a complete line of text, or you can ask for some number of bytes to be read and converted to text. Both of those turn out to be useful for what we're doing. So really, that's all there is to it. To receive, you do that, and the callback is called with the string that was read. Or you can send out a string socket. So that's going to be at the heart of your PS12 HTTP server is a string socket listener listening for connections, and then when a connection is created, you'll go through the HTTP protocol. You'll get a request coming in, you'll send a response back, and we'll go through that in a few minutes. Okay, so you'll be playing with string socket. Then there's a way to shut them down and close them. And that's all there is to know. So they're easy to use. It's just, it'll feel a little weird at first because I sort of deliberately made them asynchronous just to mirror the way the regular sockets are asynchronous. But I've made it so you don't have to worry about bytes. You just worry about strings. So before I go and look at HTTP, any questions I could answer? All right. Well, I'll be providing the string socket class. So you want to use that. All right, so now we're going to discuss, I'm not going to tell you every last detail about HTTP. I'm just going to tell you enough to do PS12. And fundamentally what you're going to have to do is be able to receive HTTP requests, decompose them to get the information out that you need to get out, let your service method run using that information, and then take the response you need to send and create an HTTP response from it, send that out. So here's an example. So remember, all you're doing on PS12 is implementing enough of an HTTP server that you can implement the Boggle. It'll support the Boggle service. So it's a far cry from a full HTTP server. So suppose that a client connects, creates a socket, and sends that request. So every time an HTTP request makes it to your server, it'll be because a socket connection was requested, the string socket listeners saw the request, created a string socket to communicate with the remote client. And you get that string socket, and for the duration of that string socket's life, its only purpose is to service this one request. When servicing this request is done, you throw the string socket away. And then the next time a request comes in, a new string socket will be created. So we're going to go through the life cycle of a request. So this comes in at that URL. This is what you will see. So you'll see something. You'll see the first line you'll see will be a get. So just the word GET. Then it will say /Boggle service /game /G0, where that's meant to be a game ID. HTTP /1.1. It'll probably say host : localhost 60,000. It'll probably say accept application JSON. So there's that first line, and then the next lines, in the case of a get, are just headers. And headers are just header names followed by a colon followed by the value of the header. And the request is always terminated by a blank line. One fine point, every line has to be ended with /r/n. Doesn't matter if you're using Windows, where that's standard, or Macs, or Linux, where it's not. HTTP protocol insists on /r/n. So be sure that you realize you'll be receiving lines with /r/n terminating it, and that when you send anything out, you need to put that at the end as well. All right, so that has come in. What do you have to extract from this to figure out? So when a request comes in, you have to figure out which endpoint am I supposed to call. You've got 5 endpoint methods. Which one am I supposed to call, and what parameters should I pass to it? So how do you look at the information that just came in here and figure that out? How does your program do it? You ask the string socket, give me the first line, and it gives you that line that starts with get. What's your server got to do? Which piece? Yeah.
You have to parse the text.
Right. You've got to parse that first line up there. So you've got to right here. You've got to look at the first word on the line and see, is it get, is it post, is it put, is it delete? So you see get. Okay, that's one thing. What else do you need to look at? Right, you got to look at this URL and in this and look right here, and that's, you know, there's that right there, games together with a get tells you which endpoint you care about, what you've got. You've got an endpoint that deals with games requests. That's a get. Okay, what else do you need to pull out of this first line of text? Yeah, you got to pull the game ID out. So really, what matters is the get, the games, the G0. And then once you've got those pieces of information, you've got all the everything you need to call that endpoint method, which you could then do, because all the endpoint method expects is that game ID. So you pass it the game ID and it does its thing, and we'll see what we do on the other end. So that's what you'll be doing, is reading the lines as they come in and figuring out which endpoint is being requested and running it. That's all done automatically for you right now, just from the annotations. So you'll have to write code to do that. What kind of code would you use to pull this URL apart, this first line apart, to extract the meaning from the good parts? Yeah?
Like a string reader?
Well, you could do, I mean, you've got a string, so you could use string operations to pull it apart. Split, yeah. Yeah, you could turn it into tokens. You could write a regular expression. So you got your choice of ways. You'll always need to know what the verb is. You'll need to always figure out what that thing is, whatever comes after log of service. And then based on that, there may be extra parameters in the URL. There may be parameters in the body. You just got to figure out which case you're in and deal with it. But you've only got 5 cases. You only have 5 endpoints that you got to choose from. Okay. So there we have it. That highlights the 3 things, the parts. You've got the request type, the URL, an embedded parameter. The arrow's pointing at the wrong thing. I'll be pointing at G0. We haven't done anything with the headers. Do we care that the host was localhost 60,000? No. Do we care that the user wants JSON back?
Yes.
Well, we care, but what if the user wants XML back? Tough. So you're just going to send JSON back. Okay? So we don't even care what the user requests. We're just going to give them JSON because we're trying to make this simple. Okay? So really, for this, you can ignore the headers. All you care about is the 3 things on the first page, first line. When you do, there's sometimes you do worry about header names, so you should know that the headers are not case sensitive, that they can occur in any order, but there's a blank line after the last header. And that's what I mentioned about return new line characters at the end of every line that you receive and that you send, except possibly the last, and I'll talk about that too. Okay, here's another kind of request. So let's suppose the client does that. And so what comes in is post Boggle service /game /G0 HTTP /1.1. Now what does that endpoint mean? When do you post as opposed to get to games?
That's joining a game.
So, right, that's joining the pending game. So you make a post for that. Okay? So let's see what's different. You got to see the post and you got to see the games to know which endpoint's being requested. Now you know which endpoint's being requested. You know that you need to find the game ID elsewhere in the URL. But there's another parameter which is the serialized object right here. You realize since you're dealing with this particular endpoint, you're going to have to find this object. Okay? So you've got headers you're going to have to look at. And the only one you care about is this one right here. Again, we're going to assume it's JSON. But what you find out, what this tells you is that after the blank line, there are exactly 79 bytes. And those 79 bytes, when decoded and deserialized, describes an object that you need to retrieve. So basically, you need to get these 79 bytes, convert to a string, turn into JSON, turn into C# object, pass as a parameter. Yeah.
You said that we can ignore the local host. I was
Yeah.
just wondering, like, because we are like the 60,000 is what we're using to connect to
Yeah.
that specific port. But once it's already sent, then you wouldn't really need that line anymore. Is that right?
Yeah, well, that's just telling us that localhost 60,000 shows up in that URL up there. It's just the request contains within it the IP address and the port number that your server is running on. But you're the server. You don't care where you're running. You don't need confirmation that you're running on port 60,000. So it's just redundant information. So among all these headers, since we're stubbornly refusing to deal with anything but JSON, the only thing that matters is the content length. So you got to grab these 79 bytes and turn it to a string, into JSON, into C# object, and pass. Okay, so there's, again, that arrow's pointing to the wrong thing, wrong place for some reason, but this is the stuff that's indicated is what you got to pull out of the request. 5 things. Now, if you were a real HTTP server, then you'd need to look at and consider all the headers. But we fortunately don't have to do that. The request body does not turn. There's no new line at the end of that. No anything at the end. It just ends after those 79 bytes. Starts right after the blank line and goes for 79 bytes. All right, you've got to generate responses. So maybe this is a response to, I guess that it's intended to be a response to the first kind of request. I don't know what this is a response to, actually. What endpoint would you send back a user token? This is for an older version of the API, even. Yeah, when you create a user, you get back the user token, but it's not in an object. It's just a string. So this is just I should have updated this slide, but so just bear with me. Just assume we want to send back an object containing the user token instead of just the string. So you've got to send back something to the response. So here's where you start sending lines of text to the server, out to the socket, to the string socket. You create a line that says HTTP/1.1. We don't do 201 anymore. We just do 200. So you say 200. OK. That's the first line. Yeah.
Is there a reason you're using HTTP 1.1 instead of like 2?
No good reason. As long as you could use a different version up there. We're using the same. It's going to be all the same. I guess when I created the slide, HTTP 1.1 was just it. So you send that first line out, and then you're sending a response, something. So you've taken the object you want to send back, which in your case would be a string. In this case, it's an object. You turn it into, you serialize it into JSON. Then it gets converted into a bunch of bytes. The number of bytes it takes to represent this is that 52 right there, the content length. So you're going to have to compute the number of bytes it takes to represent your serialized string. Then you send that next line out, you send out a blank line, and then you send back the body. So you're just sending strings out through the string socket. Okay, so that's request and response. So now what we're going to do is just go through step by step what the life cycle of a request. So a string socket has been created. What do you have to do with that string socket to deal with a request? So number one, well, even before you get the string socket, your server has to sit there and receive connection requests and establish socket connections. So what class do you use to do that? String socket listener. So you just fire one of those up, and every time a request comes in, a string socket will be connected, and a callback method will be called. All right, so a string socket has been created. Now you've got to start reading from it. How do you read the first line of the request? Yeah, you you just call the begin receive method, and the callback is called. Okay, you have to examine the first line to determine which service method is to be invoked. So you got to pull out the verb, you got to pull out the part of the URL. And we already said you could use regular expressions or something else to do that. Okay? Then you've got to, if there are any parameters in the line, in the first line, you got to pull them out. And you'll know their parameters. Once you figure out which endpoint is being targeted, you'll know whether there are parameters in the URL, and you pull them out with regular expressions as well. This is all stuff you know how to do. It's just step, 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 step. Okay? If there is a content link header, there will only be one if there's a body, if there's an object in the body. You'll have to read through the headers, and when you find the content link header, you'll have to extract the number of bytes in the object. So we call begin receive, and then you can use regular expressions to examine the lines. As you know, it'll give you back one line at a time. You're looking for one that starts with content length. So you parse out the number of bytes. Okay? If there was a content link header, you keep reading until you get to the blank line, and then you know, if the content length was 59, and now you've got to read 59 bytes and convert it to a string. How do you do that? How are you going to read exactly the next 59 bytes and get a string back? Yep. Well, we're doing everything through the string socket. Yeah?
Wouldn't every character be, is it 4 bytes?
No, every character, we're using UTF-8, which is a variable length encoding. So it's not necessarily the case. In fact, I have a test case that I have used. I won't use it for this assignment, but I've used it for the string socket assignment that I didn't give you. That would send alphas, you know, Greek alpha, which takes multiple bytes to represent. Okay? There's only one method you can call to get text out of the string socket, and that's begin receive. But begin receive has a parameter called length, you may remember. So there's an overload that lets you specify. Normally it reads bytes until it gets to the end of the line. But you can, if you pass that 52 as a parameter to begin send, then it'll give you the string that results from the next 52 bytes that it reads. So that method is designed just for this purpose. Okay, so you read those bytes. How do you going to convert those? Now you've got a string. How do you convert that string into a JSON object, into a C# object? Yeah, we've seen the deserialize method before. So we just deserialize the string, and we get a whatever object it deserializes to, or you could use dynamic here if you wanted to. Okay. Okay, so now you know what endpoint method you're supposed to call. You have the parameters you're supposed to call. So you call it. It's exactly, you don't have to change anything about the code of your endpoint methods. That's what you're doing this week. So next week you just call them. So you got your string socket code, your code that's consuming the string socket will call the endpoint method. It'll do whatever it does, manipulate the database, and it will either return it will either return normally or throw an exception in the case where you want to do something other than an OK status code. Okay? So that's just, you call your existing service method. Pretty easy. All right, now, once you've got the answer from the service method, you've got to send a response back. So the first line, what you plug on the first line is a status code. How will you know what status code to put on the first line of your response? When do you put a 200? When do you put a 204? When do you put something else? Yeah.
Each method has a thing inside of it designed to throw a certain exception.
Okay. So so your service methods are designed so that if they return normally, you want to send either a 200 or a 204. 200 if the 204 if the method is void, no content, 200 otherwise, which is okay. If your service method wants to return a different code, 407 conflict or something, it throws an exception, which is what? I forget what it's called. HTTP status exception or something like that. So you just got to catch that exception, and if you catch one of those exceptions, then you know to send back a response with that response code, as opposed to the 200 or the 210 or 204. Yeah?
How does the web server communicate? How does the web server call methods from the service? Are they in the same?
Yeah, he's asking, how does the server call the service methods? It's all going to be in one project. You're going to take your service method implementations and just copy it over to a different project, to a console project. So it's just like calling code in this, elsewhere in the project, stuff you've done all semester. Okay, so you figure that out, and you send it out with begin send. Then you got to send a content type header. So you say content type application /JSON. If there's a return value, you've got to serialize it into a string. If there's a return value also, you've got to take that string and determine how many bytes it will take to encode it, and use that answer to send a content link header back out to the client so they know how many bytes to expect. And I showed you how to do that last time. Be sure you use UTF-8. Okay. Then you've sent all the headers out. Now you send a blank line out. Then you need to send the string. So you've got your serialized string. You just send it out the string socket, and it will get encoded into the right number of bytes. Then you're done with the string socket, so you shut it down. And it says here to handle errors and exceptions gracefully. So what could go wrong in any of this? What would be how would you detect a client error? So client errors is supposed to be like a 400 type response code. Server error, internal server error, should be a 500 type response code. So let's do it the other way. What would be an internal server error? How would you detect? Yeah. He said maybe something didn't serialize or deserialize properly. Well, if it doesn't deserialize properly, I'd call that a client error. The client sent you bad data. Okay? So if they're unexpected things that happen on the data you're reading from the user, there's missing information or something doesn't deserialize properly, that's when you detect those errors in your code, unhandled exceptions or whatever, you report some 400. You pick a 400 code and send it back. On the other hand, if after you've read the user data, if you have an exception later, that's a problem with your code. That's an internal server error. So you would, again, if you have an unhandled exception, you catch it and you send back a 500 code to sort of say what happened. Okay? And you got to do this all simultaneously, because you may have a bunch of games going on at the same time. Now, that sounds bad. Somehow your poor HTTP server has to deal simultaneously with 100 simultaneous games. So what are you going to have to do to achieve that? What's it going to take to support all these games in parallel? Well, it takes good code just to support one game. What's it going to take to do 100? Well, he said multi-threading. Here's the good news. It takes no effort whatsoever. Where does the multi-threading come from?
The string socket?
Yeah, from the string socket. Basically, whenever a connection request comes, it's going to make a callback into your code on some thread and say, here's a string socket, deal with it. When the next request comes in, it's going to do the same thing. Another thread is told, here's a string socket, deal with it. So stuff is just naturally happening on separate threads. That's just the string socket listener and the socket make sure that happens. You just have to make sure that as you're processing in parallel a whole bunch of requests, that they don't interfere with each other. But how can that happen? How could separate requests to your Boggle service interfere with each other? What do you think? What about the one you're doing right now? How did you avoid that problem last week on PS10? That was multi-threading. How did two endpoint methods as they're running avoid interfering with each other? Yeah?
Using like asynchronous requests.
Well, I don't think that's not how you dealt with it last time on PS10. Yeah? Locks. You use static variables and we locked access to them. Okay? How are you dealing with that problem this week? Yeah? Well, the database is dealing with it for you. You're defining transactions and the database is doing the rest. And so you're just copying that over for PS12, and so it's all taken care of for you. As long as you don't add any instance variables, which you don't need to, this all comes for free. So what I just described, all these steps, that's just sequential code. It's sort of like writing Hello World. Except there's a lot more steps than one, but it's just a, I don't even know that you have to write a single loop. I'm trying to think. Oh yeah, you have to write it. Well, yeah, I bet you don't even have to write a single loop because of the way the string socket is designed. Conceptually, you're looping through headers at some point, but that's happening via callbacks. So it's sort of an implicit loop. Anyway, I'm sure this is way more information than you want to hear today, but it becomes very important next week. So you at least know where to look for it. Yeah?
So is the actual process, is it the callback method that gets called by the string socket is the one that actually calls the methods in the server?
Yeah.
Okay, yes.
I mean, the way it'll work is, when you're reading stuff from the string socket, you'll say, give me a line. A callback will be called on a separate thread. You look at the first line, and you say, okay, now I need to read headers. And so you'll say, give me another line. And another callback will happen, and you'll start reading headers. So essentially, every line results in a callback. You deal with that line. Ask for the next line, you get another callback. So it'd be kind of weird because you're writing sequential code, but it's actually being run on different threads each time. But that's the way the socket is structured, so I kept it. Yeah?
So we're kind of handling off the tasks on a separate thread. What happens so if two requests are made at the exact same time?
Okay. Well, the way you'll be structuring your code is there'll only be one thread at a time dealing with asking for data from a socket. It's never going to be the case that two threads are simultaneously trying to read from the same socket. You may have two threads reading from different sockets at the same time, but that's not a problem. Okay. Any other questions? Yes?
So we're using that payload object to pass things between the...
One use for the payload object is to pass through to tell the callback what it should do when it gets called. Right? Read headers, or read body, or something like that. Or you could also keep that same information in instance variables. That's kind of cool to do with that. You can do it without instance. When I say instance variables, I mean instance variables that are local to some object that holds the string socket, as opposed to global variables that are shared between. Yeah. All right, let's take a break and we'll look at something else. Okay, I had a good question at the break. And it boils down to this. Why are we ignoring that? Why are we ignoring the boggle service from the URL? You're interested in the get, and we're interested in the games and the G0, but why are we ignoring boggle service? Yeah, it's always the same. We expect it to be there, but it doesn't tell us any information we don't already know. So why is it there? What purpose would it serve if this were a real server and not just one that only deals with boggle service?
It might be running not boggle stuff.
Right. You might have a server running multiple services, you know, boggle service and chess service or whatever. So you've got to look at the whole URL in that case to figure out what's being requested. We can sort of cherry pick because we know what's being requested. All right, this is completely different. I want to go over with you again and add to the runtime memory model that's common to, the basics are common to basically all programming languages, pretty much all programming languages. And so you know that the runtime memory model consists of the stack and the heap that keeps track of, it's basically the data structure that a running program manipulates. And the issues we're going to show you, I'm going to show you how they work are variable lookup, value versus reference types, value versus reference parameters, and we're also talking about inheritance and interfaces. So I'm going to talked about the model before. I'm going to expand it a little bit and try to show you a few more details. I'm not going to show you every last detail, but I'm going to show you a lot. So let's just start with the basics, value types. So things like ints, chars, structs, whatever. Okay? Every time I create slides, I draw things slightly differently. So this is meant to represent, the stack is over here and it's growing in that direction. The heap will be out here. Over there's my code. Over here to the left, I'm telling you that this is the place on the stack where C is stored, and this is the place on the stack where X is stored. But that stuff isn't there at runtime. At runtime, there is no C or there's no X stored on the stack. You just have values stored there. But for us to look at it and understand what's going on, it helps to have this queue there. All right, so we're essentially stepping through main. So int x equals 3 stores a 3 into the current stack frame. Remember, there's an entry. This stack frame is for main, and why are there 2 entries in the stack frame? What goes in a stack frame? Well, variables are stored on a stack frame, but which variables? No.
Method call.
What's that?
The ones from the method call.
Right, all the local variables of the method and all the parameters of the method. So main has no parameters, it has 2 locals, so we have the 2 values on the stack. So we store x equals 3, then we do char c equals character c. Then we call f, and you know that when you call a method, you get a stack frame allocated for it, and f has 2 parameters and no locals, so we get d and y up here. And these are value types, and so when they're passed as parameters, they're just copied. So the 3 is copied up to y, the character c is copied up to d. So value types imply copying both for assignment and also for parameter passing. Now we change y to y times y, so that y changes to a 9. Then we change d to the letter d. And then the method returns, wiping out the stack frame for f because we're done with it. It had no effect whatsoever on any of the variables in main, which is what we'd expect. And then we change x to 7 and we're done. So that should be pretty familiar. That's just how the stack works. Keep track of variables. Now I told you that variable names are not stored on the stack, and they don't appear in the compiled code unless they're there to support debugging. Okay? Instead, fixed offsets are computed by the compiler. So the compiler is going to figure out, let's see, x here. It measures from the top of the stack. And so the compiler knows that C is stored at the top of the frame, and it takes 2 bytes to store a character. So X is stored at an offset of 2 bytes from the top, and C is stored at an offset of 0 bytes. And so in the compiled code, when the compiled code needs to look up X, it doesn't go look for X and then come over here. It takes whatever memory address is the top of the stack, which is stored somewhere, and adds 2 to it to get the address of the variable. So what you find in compiled code are the offsets, not the variable names. Okay? Now, what if we change and we have reference types? Let's go through the same sort of example using reference types. So the stack frame for main only has one variable, because there's only one. And right now there's nothing in it. We initialize it with an array, and so the array is constructed over here. And we get a reference. So that red reference means, what's stored on the stack is a reference to the thing on the heap. So what happens when we call f and we pass 2 parameters, a, the array, and a sub 1, which is right there? What will the stack frame for f look like? So there are two variables in f, so there'll be b and n will be on the stack. But what will they contain? Yeah.
Will just contain like a line. The reference will just contain the reference, which is a line to the array.
Okay.
And the primitive will be copied back over.
Okay. So the primitive is just copied up, and actually the reference is copied up. If what you're thinking is the reference itself is copied. So just whatever address is here is now there. So we got a shared reference to the same array, so that when we change b sub 0 to 2, that's going to be ultimately visible from down here. If we change n to 3, it changed up there, but after we return, it's disappeared. But we do see that change because of the sharing. So that's what you have to know. You have to understand that. For example, back in PS4, when you added a copy constructor to the dependency graph class, we added a constructor that took another dependency graph and was supposed to create a copy that had nothing in common with the original, no sharing. And a lot of people missed some test cases at first because they didn't make a deep enough copy. They forgot that objects can be shared among other objects. Okay, now let's put reference parameters into the mix. What we just looked at were value parameters. How does it change when we pass the parameters to f by reference? So we start in the same place, the stack frame for main. What's it going to look like when we call f? What will y and d contain? Yeah? Right, they contain references. I use green arrows for call by reference references. So y, this is a reference to where y is actually stored down here, and this is down to d. So when we do x gets 7, when we do y gets y times y, what the compiler has to generate is code that says, okay, go to a certain offset from the top of the stack. There you will find a memory address. Go to that memory address and pull out what's stored there. That's how it gets the value of y. And ultimately stores a 9 back there. Okay? Same thing happens when you do d gets the letter d. The compiler has generated code that says, okay, go to offset 0, find this thing. You find a memory address there. Go and store a 0. Go store the letter d at that address. And so it changes it there. Again, all this stuff is missing. It's all done because the compiler can compute those offsets in advance. So those changes are reflected down here. It calls it call by reference. Okay? What happens now if we... so the compiled code knows that they're going to be pointers instead of values on the stack. It knows which offsets contain references to somewhere else on the stack and which don't. All right? So we make this call. We're doing call by reference. And so we end up with n being a reference to that spot, the spot where the thing is actually stored. And b is a reference to this spot, the spot where the pointer, the red pointer, is stored. And so if we change b sub 0 to 2, there it changes. We set n to 3. What's going to happen? Yep.
It'll change the value of that index to 3.
It'll change that to 3. Because it, the generated code is going to say, go to this address and change it to a 3. Then we return, and we see the changed array. Okay, we know that structs are value types. So let's review what happens when they're passed by value. So we have, let's see, where's main here? There's main. So we have a struct that has those two properties, n and m. Main has two variables, one variable, which is a struct, which has two parts, n and n. So this whole thing is the struct. So we say s.n gets 5, s.m gets 7. What happens when we pass it? When we pass f, when we call f, we pass, notice we're passing s two ways to f. What's the picture going to look like there? F is getting a struct s and a ref to a struct s as parameters. See if you can predict what happens. Yeah?
First parameter will be a copy, and then the second parameter will be a reference.
Okay, so the first parameter will be, let's see, what is the first parameter? First parameter will be a copy of this. Second will be a reference down to this. That's right. So A is just a copy of this up to here. B is a reference down to this thing, that whole struct. So that when we do a.increment, so a.increment changes in. So a.increment, what's going to happen when we call a.inc? You'll change that to 6. Well, okay, I animated the call to increment. Okay. And then when we do b.increment, it's going to actually operate on this thing down here. So we call b.increment, we call it. So when we call a method on a struct, basically the struct is being passed by reference. That's why I'm drawing a green arrow here. And that one is operated on. And then we return, and then we return. So when you call a struct, this, when you call a method on a struct, this, the struct being manipulated is passed by reference. Let's do the same trick with reference types now. So there's our main method. Now we have a class instead of a struct up there. So structs are always created in place. Objects are created on the stack, on the heap. So that's what we get. We create a new C. We change to 5 and 6. And again, these wouldn't be there at runtime. They're just there for our amusement. What happens when we call F? Well, before we do any of the incrementing, how many variables in the stack frame for F? That's an easy one to answer. Yeah, 2. It declares 2 variables. Where's that? A and B. No locals, two parameters. Okay, what will A contain? See, we're passing C. Okay, it'll contain, we're passing it by value, so it'll contain a copy of whatever's here. So it'll just be a copy of this red pointer. And what about when we do the second parameter, which is a reference parameter? It will have a green arrow to here. So this is a reference, this is just the same reference that's stored down here. So this was just copied up. The reference parameter is always a green arrow to down here, which is what was passed by reference. It's a reference to the thing that would have been copied if we hadn't passed it by reference. So then when we call inc, we call this. Now when you call the increment method, when you call a method on an object, this is passed just as a reference, just as a red arrow. The reference to the object is passed by value. Then that is updated. What happens when we do b.inc? Actually, I think that's going to return. Then we're going to call it again. What happens when we call b.inc at this point? It says, okay, I got to come down here, find a reference, and increment whatever it is I'm incrementing. So it happens by a different route. The first time it just went straight here and incremented in. The other time it came down here, then went there and incremented in. Yeah?
Is there ever a reason to call a reference ref
Okay? So the question was, why bother passing a reference object by reference? Okay? If you wanted to, so when you pass it, let me go forward a little bit. If you were to create a new C object and assign it to B, so if this method here said B gets new C, you would create a new object on the heap, and then the new reference would be stored right here. So that's the reason to pass a reference object by reference. If you want to let the method change what reference is stored in that variable. Okay, there were a couple other hands up. All right, now we're into more uncharted territory, method tables. So this is one thing your compiler does. When you compile these classes, it creates what's called a method table for each class. So it's created, that's what a method table for, this is an abstract view of what a method table would look like for class B. So that first arrow, the first slot of the method table, points to the method table for B's, the base class for B, which might be the object class because it doesn't say otherwise. Okay, the next entry contains something that identifies this table as belonging to class B. Okay, then you have the methods provided by the class are listed next, and so each method will have the address of the code to call, the code to use when that method is invoked. And again, these tables wouldn't actually contain the F and the G. The compiler would just know that the reference for F is stored at some offset from the top of the table. The same thing for G. So what do you suppose D's table would look like? D also has a method table. Okay? What will the first entry in D's table be? It will be a reference to B's table, because D extends B. It'll say class D, and then what methods will it have entries for? What methods does D provide? It provides F. It inherits F, so it's got F. It provides, well, it overrides F. It provides G by inheritance, and it has a new one called H. Okay, and by the way, the method table only involves virtual methods. There's no method table, there's no entry in a method table for non-virtual methods. So that's the picture you get. So it says, okay, when F is called, run this code. When G is called, run that code I inherited. And when H is called, run this code right there. Very important. I'm just going to tell you something before it comes up. What's very important is that the methods that are inherited from B, which are F and G, are stored at the same offset in B's table as in D's table. You see that? And that turns out to be absolutely essential to this model. We'll see why in a second. So the F and the G up here, the method table for D is the same as for B, other than these two things up here, except for stuff added on the end. Okay? So if you know that you need to call the method F, and all you know is that it's at offset 0 of the method table, it's at some offset of the method table, you would find it in the same place, no matter which table you're looking at. That's what makes inheritance work. Yeah?
So if G wasn't virtual, would it not be in B and
It wouldn't be, if G were not virtual, it wouldn't be in either table. The method table is there to make inheritance work. So when you create an object, it contains, in addition to the instance variables x and y, the object always contains a reference to the method table of its class. So you create an object of type B, you get that. You create an object of type D, you get this. So, and there are lots of uses for that. One use is if you need to test the type of an object. Suppose you want, there's a test in C#. You can test, is this object of type D? Well, it just follows this reference to the table and sees it's at class D. What if you ask if this object is type B? It is. It's both type D and type B. How would it answer the question? Yeah? Right. It would come over and say, oh, that's not B. And then it would go up a level and say, oh, it's a B after all. Yeah?
Wait, so the only reason G's in that class D table right there is because it's inherited from...
Yeah, because it's inherited from B. Okay. The other reason we have that reference is so that when we invoke a method on an object, we know what to do. So suppose we invoke the method f on that object up there. Okay? How does it decide which method to actually call? Right. We call method f on that object. It comes over here to the table. It knows that f is stored at offset 2 from the top. It goes there, and it calls that code. What happens if we call f on this object? Same thing. It also looks at offset 2 and calls the overridden method. So it doesn't matter where these objects are stored. Even if this object is stored in a variable of type B, when we invoke f, we always figure out which f to call by going from here. So if a variable happens to hold one of those objects, it will always, no matter what type of object is in the variable, it will always go to the same offset in the table. It's just which table does it go to. So that's why it's important that f and g be at the same relative offset in both tables. So inheritance is a little expensive because we call a method on this object. You've got to come over here, go to an offset, and find the code. If it's not virtual, then the compiler can tell in advance what code to run. It doesn't have to be figured out at runtime. Okay? So that shows you how inheritance works. Let me pause here because this is a new thing and see. Anyone would like to ask a question? Yeah?
So in this example, we have class B and D. And then when we're actually making an object, we're using class D, which references, we're making an object of class D, which references class D. But what if we were to make an object of class B, but we, so it's an object of class B, but we initialize it as class D.
Okay. So the arrow that's used here depends on just on the constructor that was used to create the object. So if we say new D to create this object, it'll point to here. If we say new B, it'll point up there. It doesn't matter what kind of variable we store the constructed object in, it's what constructor we used. Now, this shows you some more of the overhead of object-oriented programming. You've got the method tables to sort out inheritance at runtime. You also pay this penalty. Each object carries with it that extra pointer at the top, so it takes more space than you think. Structs in C# don't support inheritance. So what savings will a struct have relative to an object since structs don't support inheritance?
No reference.
Structs are just relevant to that class that they're stored in.
Yeah, so it doesn't need to carry around this reference because that's just there because of inheritance. So it means the object, there's less space. So structs are typically pretty small already. So we don't waste a lot of space, a relative lot of space on a pointer. And then the method calls are faster because they don't have to be figured out via the method table. Now, interfaces make things even worse. So calling a non-virtual method takes a certain amount of time. Calling a virtual, and because when you write code that calls a non-virtual method, the compiler can figure out what code needs to be called in advance. When you call a virtual method, I just showed you what has to happen at runtime. Java, by the way, doesn't have any non-virtual method. They're all virtual by default. C# wants you to be able to decide to make things non-virtual so you don't pay this cost. But when you call a method through you have a variable that's of an interface type and it contains an object and you've got to call a method on that object. That's where things get a little more complicated. So there's a method table for C. And it also has to contain within it sort of a reference to a list of the interfaces that it implements. Okay? So this method table implements, it implements class C, it provides these virtual methods, and it provides those two interfaces, I and J. Each interface then, each of those tables then contains a reference to the, I didn't draw them all the way because it would have been too confusing, but this would contain a reference to this method right here. And that H would point down to here, and the F would point to there. It points to the methods that are to be called when you invoke a method through the interface. So now think about it. We have an object of this type, and let's say but all we know about it, we don't know the type of the object. We just know it's, the compiler just knows that there's a variable of type I, and we're invoking a method on it. Yeah?
Would the interface map change if we said, instead of class C and like I, J, we write like J, I?
It might be in a different order.
But other than that.
Yeah. So what's it going to take now when we call a method on all we know is a variable is of type I, and we're calling a method F on it. What's going to have to happen? Let's see if I've got an object. Okay, there's our object. So we got this object. All the compiler knows is that it's at runtime it'll be some object of type type J, let's say. What code will the compiler have to generate? Yeah.
We'd have to go into the class and then see if there's any pointers out. And then
Right. So it'll have to come over here, then it'll have to go look at the interfaces until it finds one that matches. So if this is a variable of, let's say this was a J variable, it'll have to look for the J interface. And if we're calling F, it would then follow back down here and find the code it's supposed to call. So it's more expensive still than calling a virtual method. So in the first case, back on the previous slide, we know that the variable is stored in an object, in a variable that's declared as a class type, like the variable is of type B. In this case, the object's stored in a variable of type J, where J is an interface, and it just makes it more complicated. Have to go searching around for the right method to call. So there's extra cost there as well. So fastest are non-virtual, then the virtuals, then methods that require looking at things through an interface. Yeah?
So it points to interface I, which then points to interface J, or
Yeah.
I'm just trying to figure out how that works.
I just drew that as a linked list. C implements some number of interfaces. In this case, it implements I and J. Now, if some other class implements I and J and K or whatever, it would not point to those as well. It would have its own separate tables for I and J and K. Because their job is simply to point back to the methods that should be called when you're calling through the interface. Yeah.
Would it just be like trying to match the name of the interface to the object? Or like
Yeah, essentially, yeah. And it's a little faster than I'm letting on here. You can imagine if you had a big, long list of interfaces you implement, in this linked list, it gets pretty expensive. But that's just a detail I've suppressed. It can be organized more efficiently. But fundamentally, you have to search for a while to find the right method to use. Yeah?
Is the order of the interfaces trivial, or could you actually speed up runtime if you had an interface you use more often appear?
Yeah, the order doesn't matter except for efficiency. So yeah, you could put the one that's used most often at the beginning, if indeed you're using a linked list. You don't have to use a linked list, just some sort of collection of information about interfaces. Okay, so I told you I was working at a high level here. This looks like pretty low level detail. Well, this is just what I was non-virtual, virtual through an interface, and relative efficiency. That's the whole truth in .NET. So this center thing here is method table. And let's see what we can pick out here. Here's interface stuff over here, and I don't even know what all this stuff is. So you got interface maps, class maps got to be somewhere. Well, that's the method table. So that is the runtime structure that .NET is keeping track of just to support, inheritance and virtual method calls and such like that. So that's one structure. That structure is generated by the compiler. It's sitting in your code somewhere, compile code. You've also got the stack and the heap somewhere that are all cooperating. So the story gets fairly complicated. So the stack and the heap model is common to all languages. Virtual method tables, typically common to languages that support inheritance. But the exact detail of how it's done depends highly. I'm sure Java's runtime structure didn't look anything like that. Okay, so that's more of the story on how programming languages work. Okay, have a good weekend, and see you next week.
Two quick questions for you, Ben. So when we're talking about the overhead of like